Hello, ladies and gentlemen. Welcome to our video. For today's video, it's all about game theory, and we'll give some of its example. In this video, we'll give you a little introduction about the topic, and after that, we'll give some examples. Let's move on. Our topic is game theory. A game, in the mathematical sense, is a situation in which players make rational decisions according to defined rules in an attempt to receive some sort of payoff. Game theory is the branch of mathematics which focuses on the analysis of such games. Game theory can be divided in two main subdisciplines, the classical game theory and combinatorial game theory. Classical game theory studies games in which players move, bet, or strategize simultaneously. As a result, players often find themselves ignorant to certain aspects of the game. Players of these games are more likely to depend on prediction and chance due to his lack of information. Example includes poker or rock, paper, scissors. While combinatorial game theory, on the other hand, is a study of two-player games in which player has complete knowledge of all aspects of the game throughout the entirety of the gameplay. These games are usually played on a turn-by-turn basis and do not typically involve elements of chance. Examples include chess or checkers. Furthermore, combinatorial games are said to be impartial if all players have the same set of possible moves from each position. Otherwise, the game is said to be partisan. Classification of the games. In addition to the two classifications presented above, games can be classified in a variety of ways. One of the most obvious is to classify a game by the number of players. It is common to describe a game as an n-person game, where n is an integer greater than or equal to 1 representing the number of players required to participate in a particular game. Games can also be classified based on the total possible winnings, a constant sum game or zero-game sum game, in which the sum of total possible winnings remains constant no matter what actions the player take. That is, the sum of the winning gain by some players must be equal to the sum of the other player losses. Moving on, the Nash equilibrium. The Nash equilibrium is a concept which was originally presented by American mathematician John Nash. A non-cooperative game is said to be a Nash equilibrium if no player has incentive to change his individual game strategy after considering the strategies of all players.
Okay, now let's do some more complicated game theory problems with some payout matrices that are not 2 by 2. So the problem is Intel and AMD. The following normal form game depicts the pricing rivalry between Intel and AMD for their newest top of the line chip. Each company considers 5 possible price levels: $449, $339, $349, $299, and $249. They decide their prices simultaneously. Monthly profits in $1 million are. Next slide. So a payoff matrix that what you see here is a list of payouts given the two strategies of each player. Typically in a business context, they're going to be companies. So the problem is all about the Intel and AMD.
So to continue, as you can see in the table, on the left side, we can see Intel, and on the top one is AMD. And it could be anything most of the time we make, and we analyze these games where they're choosing simultaneously, meaning at the same time.
So here we've got a pure pricing game, Intel and AMD. Both are making chips, but they need to choose simultaneously, and we need to choose a price So AMD can choose all of these prices along the top, and Intel can choose these prices. Here, the way to read this, the first number in the payoff matrix belongs to the left player, Intel, and the second number belongs to the top player, AMD.
Okay, so let's start analyzing this using Intel. As it looks complicated, but in reality, there's just strategies that we can apply to solve this kind of problem. So if AMD chooses 449 as their price, what's the best payout for Intel? So the best payout for Intel is 230 because it is the highest payout. And if AMD chooses 399, what's best for Intel? It's the 210. If AMD chooses 349, it's 180. And if AMD chooses 299, the best for Intel is 140. If AMD chooses 249, 120 is the best for Intel.
So to continue, no, it looks like Intel never picked 299 or 249. So we would say that those are dominant, or 449. We would say that those are dominated strategies. They've been dominated by all the others.
Okay, now if Intel chooses 449, the second number we're going to look at which one is the best for AMD is the 70. For the 349 prices, which one is the best for AMD? So it's the 50. And for the 299, it's the 35, 25, and also the 20. And now already we got a Nash equilibrium, which are the 140 and 35 in the price of 299. Looks like AMD would never pick 249 and 449, so those are dominated strategies, and those can be eliminated as well. We have a Nash equilibrium in this game. So it is possible to have a game where there is no Nash equilibrium. So that's how to solve this one. That's
So here's another short game I found. This is called Information Game. It states that considering the following game where nature determines if payoffs are as in G1 or G2 by equal probability. So as you can see in our screens, these are the G1 and G2, and you have 4 players in total: player 1, player 2 for G1, and player 1 and player 2 for G2. So players move simultaneously. Player 2 knows which game nature has chosen, but player 1 does not. Please answer the following questions.
the question is, what is the strategy space for player 1? What about player 2?
So I got a solution for that. So remember that the strategy in Bayesian game must specify an action for each type. So since player 1 does not know the game that will be played, he can only specify one action. So player 2, however, can specify an action for each realization of nature's action. So therefore, the strategy sets are, we have here the S sub 1 equals brackets T, M, and B. And S sub 2, we have equals brackets the quantity L, the quantity L, C, the quantity L, R, quantity C, L, quantity C, C, quantity C, R, quantity R, L, quantity R, C, and quantity R, R.
So to find all Bayesian Nash equilibria, once we know the possible strategies for each player, we can draw the normal form representation and solve for the Bayesian Nash equilibrium. So the normal form for this problem is presented in the table below. So as you can see, player 1, player 2, TMB, LL, LC, LR, CL, CC, CRR, LRC, and RR. So these are the given data. And the way the payoffs in the table above are calculated is analogous to the method used in the problem set. For example, when player 1 strategy is T, player 2 strategy is L, L. and the player one's expected playoff is presented in the formula E1 multiplied by S1, S2, which is equal to 1/2 times 2 plus 1/2 times 2, which is also equal to 2.
I see. There are two Bayesian Nash equilibria in this game. The first Bayesian Nash equilibria is the bracket quantity T and quantity R and C. And the second Bayesian Nash equilibria is the bracket quantity M and quantity L and L.
So that's it. I hope that you learned something from our video. Thank you guys and see you in our next video. Bye.